I'm teaching this time. Differentiability. All the word differentiability means is can we do the derivative? And what I was trying to get through to you at the end of the week you were here before was doing the derivative means finding the tangent slope. So the question we're really asking today is, can we find the tangent slope? And the answer is yes, almost always. Almost always. Can we take the derivative? Can we find the tangent slope? And today's lesson is just, here's a few times where you can't take the derivative. Okay? And there's one test hint in the middle of all this, because I've got your Unit 3 test ready to go. As we have seen, some functions have points that we cannot find the derivative. The following diagrams illustrate some ways in which a function can fail to be differentiable at a point. All of these functions that I'm going to do here are not differentiable at x equals 0, and we're going to get to know the names of why they're not differentiable. This thing here, when you've got a point like that, is not differentiable. The slope coming in from this side's -1. Slope coming in from this side's +1. At that corner, there's no way to say what the slope would actually be. There's no way to draw a perfect tangent slope there. So this is called a corner. That's it. That whole slide, just to know that word. Maybe you already knew that word. Corner. Here's the reason the function is not differentiable at x equals 0. Different slopes from each side. That's all I really need to know about it right now, but I do want to say it's more important than that to know that what happens to the derivative is it goes from -1 on this side to +1 on this side. It jumps, and when a derivative jumps like that, you get a point that's not differentiable in between there. If you want a real-world example of what that possibly means, it's my train example again. You can't go from velocity -1 to velocity +1 instantaneously without there being a problem. That's what differentiability is really talking about is there's a little problem there. Yeah? You can't just have a point like that. The only way I can think of to go from -1 to +1 would be to run down the train tracks. And at some point, if the train comes, you can instantaneously go from -1 to +1. Okay, you physics people. No, you can't actually go instantaneously. There's this moment, this millisecond. If you slowed it right down, what a gross video this would be, right? You could slow it right down where you'd see the train impact my forehead, and then I'd slow down really fast and then start going the other way. There would be, it would happen in a millisecond, but there would be a time where I was changing velocity, where I was making impact. If you've ever seen one of those golf ball videos where you see a golf ball that is compressed all on the one side here, there is this moment where it accelerates out smoothly, but over a very, very small period of time. It's got to be smooth. There's differentiability. It's got to be smooth, and this is not smooth. It's pointed there at the corner there. Questions there? Next, this thing's called a cusp instead of a corner. How will you know a cusp? The reason it's not differentiable is slope goes to infinity on both sides. Is that weird to say it's going to infinity? Let's see if I can do it. I don't know. I'm trying to make a great video here, so I'm going to get out a ruler. Normally I just take a hand ruler. We'll see if this works. Ruler. Wow. I'm going to reset this computer a little later. Is this ruler going to let me do it? Oops. Oh, there's the angling. Oh, it's being stubborn. Oh, maybe. Oh, maybe. Do you see, if I just look at the slope right there, is it going to, come on. There. Oh, hey, got it. Do you see how the slope is sort of large there? If I move that ruler in a little closer to that 0, though, you see the slope has got, where's the twist point? Oh yeah, here we go. Slope's got more as I get closer to 0. And as I get closer and closer to 0, that slope heads up to infinity. See if I get really close to 0. I'm getting control of this thing now. Really close now. Twist, 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 twist. Last one. You see? Now the slope is really close to infinity. As you get closer and closer, this thing heads to infinity both sides. That's different than a corner. Well, it's subtly different than a corner. Corner heading to two different slopes on each side. Okay, that's enough. Get out of here. All right. Corner, two different slopes on each side. Cusp, infinity slope on both sides. Subtle difference. I'll agree. Okay? Questions about cusps? It's tough to stay with my mask on. Cusp. Next one. Simpler, I think, to talk about. This is just infinite slope. Reason it's not differentiable, there's a vertical tangent at x equals 0. It's similar to a cusp in one way, is that it's heading to infinity from both sides, but you'd almost think, oh, it's smoothly going to it. It's not like a corner, it's going to infinity on both sides. But you can't have infinite slope. You can't be going straight up like that and be able to talk about slope. Say, how much are you going up by at x equals 0? How much are you going up by? You're going straight up at x equals 0. Questions there? You know this one, jump discontinuity. Reason it's not differentiable. Can't draw a tangent line when the thing's discontinuous there. There's no way to really draw a tangent line. You say, oh, well, look, it's slope 1 on the, or slope 0 over here, and you go slope 0. I know, but how would you draw a tangent? The limit's got to exist from both sides. I can't come in from both sides. So when you lose continuity, you immediately lose differentiability there. Other types of discontinuity include holes. Can't draw a tangent line at a point that isn't there, and vertical asymptotes. Those you've seen before. Hopefully you're not all that surprised that the derivative is not going to work out at those kind of points, which again aren't technically called discontinuities by your textbooks, those two things. They call them domain issues, but I sort of think that's nitpicking on what word you're going to use there. Questions there? Determine all the points where these functions are not differentiable. A and C should be pretty obvious. I'm not going to use anything new there. Where B's got a little bit of a problem to it, and we got to talk about B a lot. And then I'm basically done. Just showing you something on the calculator for that. Is there a point on A that you can see would be not differentiable? I can identify it without doing any work. Right. Yeah. X equals -7. That's the point where it's not differentiable. So technically it's not x can't equal -7. The answer is x equals -7 is where I can't take the derivative. Now, it says also state the reason it's not differentiable. So I got to do just a little more work here because I'm not positive what kind of problem this is. I've got it narrowed down. It's either a vertical asymptote or a hole. I got to factor the numerator. That's what I get on the numerator is x plus 7, x minus 2. Those cancel. Therefore, it's a hole, not a vertical asymptote because the factors cancel out. That's simple. It cancels out. You can still find the limit here because it's a hole. but you can't find the derivative. I'm going to skip B because that's the long conversation. I'm going to go over to C because C is not too bad to talk about. Not differentiable at x equals 2. Why is it not differentiable? These are lines. I can recognize them. The slope of this one is negative 3. The slope of this one is 2. So I'm just going to write, hey, different slopes. And if you're really with me, now your question is, yeah, but what if each side is like not a line and I can't just look at it and get the slope? I'm like, hold on. Brace yourself. By the end of the week, they can put just about anything there and we'll be like, find the slope. Right? We got a taste of what that looks like in the derivative lesson is that, hey, we're just going to find the derivative of anything. And we'll get better at that as the week goes on. Oh, this thing's a real problem. A real problem. Here's the weapon you need. What color should I write it in? So you're like, oh, this is important. I've been using red. I wish I could switch over now. Important color that you can see. Well, all I can do is go with blue. That's all I got. No, purple. Purple writing. Extremely important. If it's going to let me do it. Yeah, purple. Extremely important to know this. This makes a certain problem in math, which is very difficult, actually pretty easy if you know all this. Y equals x squared sort of has this shape. Are we good so far? You're supposed to know the parabola sort of has this shape. Yeah? Y equals x cubed sort of has this shape. I say sort of. I'm not trying to make perfect graphs. I'm trying to say this is what this thing kind of looks like. From that, I can get two other graphs. Y equals root x sort of does what y equals x squared does, but it does it sideways. And then this one. Y equals third root of x. Sort of does what this one does, but it does it sideways. That's a valuable weapon. Because it works for all the even and odd powers. You go, oh, what about y equals x fourth? Oh, it sort of looks like that. What about x to the power 5? Well, it sort of looks like that. All the odds and evens sort of have that shape. Do they take off faster? Yeah, but the shape is basically the same. So now, two more graphs. Y equals fifth root of x. Sort of looks like this. Sort of looks like the x cubed graph, like that. And now the big one, this one. Y equals absolute value of fifth root of x. Way down over here. See, the negative side became positive. If your brain's exploding, you're like, what? You really need to be able to make this jump. It really helps. Did I switch to orange? To be able to go, oh, there's y equals fifth root of x. Or absolute value of fifth root of x. The negative side flipped over to be positive. After all that, can we finally answer if this thing's not differentiable somewhere? Or, yes, so it's not differentiable at x equals 0. And what is this thing at x equals 0? What's the word? Cusp. Thank goodness I delayed. For just a second I was like, okay, well, it's only a few words, new words this lesson. You really need to know the word cusp. And then somebody knew it, okay? So that's new thinking. You know, you could do x squared before, maybe you could do x cubed before, but now I'm using that to expand out to fifth root of x and the absolute value. Any questions on that mess? There are other ways to handle this question. And we'll have a great way to handle it by Wednesday afternoon. Yeah? So I introduced this way for now to go, well, we have some ways to handle this already. More time here? 2 more slides, all calculator stuff. And then I'm done till 12:25 when you write your test. And maybe we'll see. We'll see what's left of you after the test. I'd like to go again, but we'll take that as it goes. We'll see how it happens. I've tried to be kind on this test, folks. It's another coronavirus test. It's like, just keep your foot off the gas pedal, Mr. Todd. Like, just let us get warmed up here. Differentiability and local linearity. Okay, let's just talk about the planet Earth for a second. Earthlings, humans, were fooled for many hundreds of years about the shape of the Earth. They thought it was flat. Why? Because it looks really flat. Until you take a really good look, it looks really flat. Even though it's very curved, locally we can't tell the difference in the curve. It takes a long way before your eye can see it. Before a measurement device could see it, before a bullet could tell, like if you just shot bullets all day and measured where they go to, you could actually use bullets to go, oh, the Earth must be round. You know, you could actually do that. You could actually get that calculation going. But really, the first real time that someone noticed something was watching ships go off to sea. So just imagine somebody watching their cousin go off to sea. They're going, sailing the ship off to look for America or just to look for spices or whatever, you know, whatever stupid thing they thought was interesting back then. And you just watch and you're like, okay, bye, bye-bye. And you're watching, you're like, and then you watch the boat sink. You know, if you watch long enough. You're watching, and it would disappear. You know, that's a long way out. You have to have good eyes, or maybe even a rudimentary telescope. And you're like, the boat sank, the boat sank. Then, if you were watching later, you'd see it come back out of the water, back over, and come back. See, you could actually watch it go over the edge of the horizon. Tough to do. It's a long distance, but it's possible to actually see something do that. Now, water is very flat. It's not like mountains. If that happened at land, you'd go, oh, well, he went over a hill, right? But on the water doesn't do that. And you just go, uh-oh, you know? And that was the first real hint that the Earth is round. You can also do some calculations with the moon and so on. There's some ways to calculate the difference in the size of the moon at when it's down here at the sunset versus straight up. And some old philosophers did some stuff like that where they said, oh, it's got to be round. But locally, it's flat. If you zoom in far enough, the Earth is flat right here. It's not. You know, from here to the edge of the parking lot, the Earth curves, but like what, an atom or two maybe. I don't know, like not enough that you could really notice it. You wouldn't walk to the other end of the parking lot and go, oh, what's going on here? You know? It's so unbelievably big that it curves and we don't even know it. That's what's going on here. If it's going to be differentiable, it's got to be smooth, which means if you zoom in far enough, they've zoomed in at x equals 2 here. There's x equals 2. If you zoom in a little closer, it looks like this. You zoom in a little closer, it doesn't take long before it's just a straight line. Locally, like if you get close enough, not enough difference between here and here to really matter. Is there a difference between here and the edge of the parking lot? Yeah, there is a difference, but not enough to really matter. It doesn't come up in any real calculation of the situation. So, zooming in to see differentiability, you don't have to do this. Watch me do it. I'm going to do 2 different functions. I know what it's going to say here, so don't even worry about that. If you want to do it later, that's fine. I'm going to go through the whole investigation here. Let's talk about 2 different functions. I'm going to go menu. I'm going to switch over to my computer because the pen's being difficult. So I press menu and I go to 5 for graph. And I'm going to graph, absolute value. Some of you texted me questions about where to find absolute value. Your calculator does have absolute value. You've got to go in the catalog. I go Shift 4, and it gives me every single command, I believe, that the calculator can do. And there's absolute value right there, see? And when I click on it, it says ABS for absolute value, which is not what I want. So I must be in the wrong mode here. Let me just delete that. Menu 1. Go into Setup. Go into Math mode instead of Linear mode. Let's try that again. Menu, 5 for graph. Go into the catalog. Go down to absolute value. You better work, you silly thing. Oh, it's saying absolute value again. That doesn't do that on my calculator, my hand calculator. So that's one of the differences of this emulator on the screen. But anyways, absolute value of x plus 1. Enter. I hope you sort of know what's going to happen here. Do you see that graph there? Is it too small? Here, I'll zoom in for you. Zoom in here. You seeing it better? Oh, maybe you can't see it. Zoom in. I'm just playing games here. All I'm really trying to do is zoom in on that corner. Do you see that y equals absolute value of x plus 1 has a distinct corner there? And no matter how much I zoom in, so here comes zoom in, more, zoom in. It doesn't matter. No matter how much I zoom in, that slope goes from -1 to +1, and it jumps there. That's the important thing, is the amount of the slope actually jumps there. And so it doesn't matter. You keep zooming in. You see, it's not getting any less cornerish as I go in there. It's a corner. It's a pure corner. Let me just go zoom. No, V window. V window, standard. Ooh, back to the regular window. Exit, draw. Okay, so there's the absolute value. Instead of drawing that graph, I'm going to draw something different. What am I going to do? Delete that graph. Okay, so here, up here, F2, F1. New graph, the one they say. They say also graph square root, bracket, x squared plus 0.0001 plus 0.99. Enter. Draw. And you think, oh, it's the same graph. Yeah, it looks the same. It looks very, very similar, but I'm going to start zooming in again here. Zoom in on that corner. You see, it still looks cornerish. You're unimpressed. You're like, yeah, whatever. Zoom in. Zoom in. Can't see it yet. Zoom in. Are you seeing what's happening here? Zoom in. You can't see it yet. Zoom in. It's taking a lot of zooms. Just like it would take a lot of zooms on the Earth. You got to zoom in a long time on this particular graph. Unlike the oh, now you can see it. Didn't happen in absolute value, but it happens on this one. You see what's happening? As I zoom in farther, this graph doesn't have one of those corners. It's different than the other graph, and big, it looked the same, but as you zoom in, it's not a corner, and it gets better. Here's what the big point of this part of the lesson. If I do this just right, and you're right with me, you might totally get it, and you might not need any more information about this. Zoom in. I got to do a couple more zooms, and something awesome is going to happen on this screen. Zoom in. Oh, it's almost happening. Zoom in. Oh, it's almost there. Zoom in. Oh, one more. Zoom in. Oh, one more. Zoom in. If you zoom in far enough to this function, it's flat. Or as flat as this screen can show, just like the Earth is as flat as I can perceive locally. If it's going to be differentiable somewhere, it's going to be locally linear. If you get in, zoom in close enough, it's going to be linear in there. No jump, no switch of the slope. That's what that whole investigation goes to show you. And it's important to see that once in action, not just someone telling you about it, to see that graph all happen. So with all your spare time that we've given you in the last little while, later you might want to try that investigation. But the investigation just does what I just did there, exactly what I just did there. Oh, and that's the end of that lesson. Any questions about differentiability in general? More time on any of that?